Section 4.2 of your book is all about the distance formula, and that's how we're going to start Chapter 4. So, we are definitely going to need to talk about the Pythagorean theorem, and then we're going to get to the distance formula, hence the goal. So, right triangle, yes, has a 90-degree angle. Interior. I suppose if there's an exterior one too, but anyway. And Pythagorean theorem. Okay, so let's actually draw a right triangle. Let's call that a 90-degree angle. Yes. And if I label the sides of this, I'm going to call this side A, and this side B, and this side C. Okay, then a lot of you probably already know the Pythagorean theorem, or at least have heard this. And I'm going to write it like this. If on a triangle, a squared plus b squared equals c squared for the side lengths of a triangle, then the triangle is a right triangle. That triangle is right. That's a very right triangle. No, that's a wrong triangle. Anyway, I think that's amazing that they gave it that nomenclature. However, so I also want to mention that this is actually kind of a definition, and what I mean by that is if the triangle is a right triangle, then this will happen. And if this happens, then we know that the triangle is a right triangle. So I write it as if this holds, then the triangle is a right triangle, but it also goes in the reverse logic of if the triangle is a right triangle, then this will happen too, okay? So just to put it out there in terms of logic and when we can use it, when we can't. All right, example 1, similar, also, I mean, this is our geometric term for proportional. Right triangles. Number 1, use a ruler to draw a right triangle with side lengths of 3 centimeters, 4 centimeters, and 5. Okay. Now, I don't expect you to have a ruler at home, okay? But I do think that something that I have done in the past when I am in a bind for a measurement tool is I will actually just pull up like a true centimeter on whatever screen or device you're using and actually use the side of my page as a ruler. Okay, so just so you know, to make a makeshift ruler at home, that's how I would do it. Now I have taken my kids' ruler, okay, and this is from a math conference, of course. I wouldn't dare go there now, right now. So, but centimeters, yes? Okay, so let's suppose for fun, so we're drawing a triangle with a side length of 3 centimeters, 4, and 5, yeah? All right, so if I go 3 centimeters, got it, so this is 3 centimeters. And then, I don't know, let's go 5 centimeters or 4 centimeters. Let's go like this and build, 4 centimeters long? Got it. This is 4 centimeters. And then let's see if we connect this to build a triangle Uh-oh. Uh-oh. Okay, so connect these two ends to make a triangle, and all of a sudden that is just under 4.5. 4 4/10 it looks like. So okay, so this was not the correct side length. So we got 3 and we got 4 right, but then this one didn't work out, okay? Which means that somehow my tilt is wrong, yeah? Like maybe I tilted this one too far up or too far down. It looks like I tilted it too far down, shortening this purple side or this third side. So let's see if we can redo this so that we really do get a 5 centimeter length. Okay, so let's see. Let's retry. Okay, 3 centimeters. And then I'm going to push this up so that this is longer. And actually, maybe what I could do, oh, let's go with the, so push the green side up. And, okay, there's 4 centimeters. And now let's see if this worked out this time to be a length of 5 for that third side. And lo and behold, looky there, it did the job. 5 centimeters in length. Yeah? But I want you to notice that it looks like this might be a right triangle. It says draw a right triangle, and it looks like it might be. It looks like that is probably a 90-degree angle. But in order to make sure that's true, let's go ahead and use the Pythagorean theorem to verify this. Okay, so in number 2, let's make sure that happens here. Okay, a squared plus b squared equals c squared. So these must be the shorter sides because when we add them together, it equals this. So these have to be the shorter two. Okay, so, right. 3 squared is 9, and 4 squared is 16, and does that equal 25? Yes? Okay, so it actually does satisfy the Pythagorean theorem, so we do know it's a right triangle, and it looks as though there is the right angle. Okay. In number 3, it says double the side lengths of the triangle in problem 1 and draw a new triangle. Label the longest side as the hypotenuse. Ooh, here we go. Okay, so just so that we're clear, because we see in the Pythagorean theorem that these two must be the shorter sides, then this one is clearly special as being the longest side and hence gets the name hypotenuse. The other two, what are they called? Legs? Nonetheless, so I just wanted to let you know this terminology, right? Longest side of a right triangle. Okay, double the side lengths. I'm on it. It's probably going to look like this, just twice as big. So, can we fit this on the page? It's probably going to have to go through my writing. Who cares? Let's see. Okay, so we got 6 centimeters vertically. Whoops. Looks as though you can't see my full thing. Here, let me scoot that up. There we go. Okay, 6 centimeters vertically. Check. That's double that one. And 8 centimeters horizontally. Okay, so let's double that and make it 8 long. That is a little bit too long. Hopefully this works out. 8 centimeters. And knowing that this was just a smidge too long, hopefully this doubles to being 10 and they will connect. It was just a little too long, I remember saying that. Okay, so about there. Uh-oh, I used the wrong color. I used blue again. My bad. Oh well. Okay, let's remeasure this. 8. Yes. So I see that the 8 is actually lining up where it actually could connect. And that was just a smidge too long. Okay, and this one then was 10 centimeters in length. Okay, double the side lengths and draw a new triangle. Label the longest side as the hypotenuse. Yes? And I'm noticing that this just got magnified, right? It's like, just like even a lens drawn to scale. And that's what happened here. It looks like the same exact thing without the smiley, but just bigger. Okay, so my guess is that this is also going to be a right angle, but I bet we're gonna have to verify that. Okay, so let's verify that using the Pythagorean theorem. It says, show that the side lengths of this new triangle satisfy the theorem. Okay, what was it? 6 squared is 36. 8 squared is 64. And the question is, does that equal 10 squared, which is 100? 90, 100. Yes. Yes, it does. So we were right. This is a right angle, and these do match in a lot of ways. The angles are all the same, and the shape itself is incredibly similar, hence the name similar triangles. And really, it's just proportional, right? We doubled every side length to create the new triangle. Okay. Now create another triangle similar to number 1 and number 3 by taking half of each measurement of the sides in 1. Well, half of 3 is 1.5. Okay, so it is 1.5 centimeters tall. Got it. And it is, well, half of 4 is 2. So this is 2 centimeters long there. So 2 centimeters. And then half of 5 is 2.5. So hopefully these connect at 2.5. And they sure do. So, yeah, 2.5. Got it. Okay, so we just scaled it down by half instead of doubling it up. Show that this is a right triangle. Well, if we're going to show it's a right triangle, then we have to do the squaring of the sides. Oh, good God. All right, I have the two shorter sides. 1.5. I'm going to have to write it out before I can. So 1.5 squared plus the other short side is 2. And the question is, does that equal 2.5 squared? All right, I see calculator business at this point. Right, 1.5 squared, 2.25. By the way, there is a squaring button on the TI graphing calculator. Otherwise, you're going to be needing this button right here. So here's what I mean. Let's square 2.5 quick. Okay, so I'm putting in 2.5, and then I'm going to use the caret. That creates an exponent, and then I'm going to tell it to square it, and then I'm going to hit enter. So in case you don't actually have a squaring button, know that you can still do that. This upward pointing arrow, that means create an exponent. 2 squared is 4. And does that equal, I just squared 2.5 in the calculator and I got 6.25. Yes, it is. 2 1/4 plus 4 is 6 1/4. Yep. Looks like money, but it's not. Centimeters. Okay, so show that this is a right triangle. It is a right triangle because it satisfies Pythagorean theorem. So, yes. Uh-oh, I forgot the A. By Pythagorean theorem, yeah? Okay, so we can actually mark it, boop, as a right angle. So let's talk about the fact that these were all similar in some regard. So to me, 2 similar triangles, or more actually, similar triangles, they are triangles with equal angles and proportional side lengths. So similar triangles have equal angles and proportional side lengths. Okay, so just so that we're crystal clear, I feel like we have 3 right here. And then there's one that is definitely not. So if I were going to say similarity, okay, and let's make a little tiny guy, right? Okay, so in terms of similarity, right, this one scaled down by 2 created this similar guy, and this one scaled up by 2 gave this one, and we could shrinky dink or scale up, scale down as much as we wanted and get similar dimensions. But one thing that was always remained the same is this angle. So if you look at this angle right here, that is the same as this angle right here. Same. Okay, maybe here. Yeah, and that is also the same as this angle right here. All the same. Boom, boom, boom. Exactly the same amount of rotation. Similarly, the other corresponding angles are also equal. It's just that this sides got scaled up so that it looks like, you know, a magnification or a shrinky dink of another. So, couple of remarks. Okay, any triangle scaled up or down by the same amount will create a similar triangle. So, any triangle created by scaling all sides up or down by the same amount will create a similar triangle. Okay, just to squeeze it in there. And then another remarkable thing is that means that if this works for all triangles, then in particular it worked for the ones that we were working on. So a right triangle scaled will still create a new right triangle. Yeah. So when we verified one and then we saw that the others were proportional to it, then we really, didn't have to check it, but it's nice that we could check it and verify that this is really happening. Okay, let's take a peek at example 2 here. Distances. So this comes from your textbook. Rank each of the following paths by shortest to longest distance traveled without using any measurements. Oh my, oh my. Okay, Um, so, right. Here we go. So I look at A to B. So these are the instructions from your book, and I realized that I had thought about changing them, and I might. So even though there aren't any measurements, I'm still going to use some relative measurement. Okay, so let's suppose for fun, in this first picture from A to B is 5 miles or something. So I'm just making up an arbitrary length. So let's suppose for fun, this is 5 miles. And yes, I just made that up. And then I look at these other ones and I'm trying to figure out, okay, well, definitely the first one has got to be the shortest distance, mainly because we see that in the last one, right, we know from the Pythagorean theorem that from A to B and then this other distance, this vertical distance, those are shorter than the hypotenuse. So I know immediately from the Pythagorean theorem that this is a hypotenuse, and that those are the longest side. So I know that this one is definitely longer than the top one without any measurements, as a matter of fact. Oh boy, I see. I put it here. Okay. No, I'm not going to white that out because I'm just going to write it as I see number 2. So this is a hypotenuse, meaning that it definitely is longer. And then this one, I'm thinking, well, I'm having a hard time ranking this middle one to this last one. We definitely go away and back, meaning that it's not the straight shot between the 2 points. So we go a roundabout way to get from A to B, which is totally, applicable. We do this all the time with our roads. Like, we don't have like a direct road to everywhere. So, so the question is, which is more, the second one or the third one? Well, when ranking these, I definitely see that this top one is the shortest. And then I look at these other two. Shortest. Okay. And I'm like, well, it's a guess. It's an educated guess. But my guess is that the second one is the longest. That's my guess. Okay. Rank each of these without using any measurements. Well, it's probably going to be some error in here, but I look at how much pitch this has, and it was similar to this. So I'm thinking that one's the longest, and this one is medium. Oh, how was the path? Fair to medium. Okay. Suppose the distance from A to B is 5 miles. Okay, I've marked it. And estimate the distance traveled along each path. Ooh, all right. Now I'm going to actually use measurements. So, let's see. Ooh, in centimeters, distance from A to B. How much is that? What if I measure it in inches? Is it more precise? Heck no, no way. Okay, so centimeters it is, more precision. I see that it is 6.6 about. Okay, we'll go with 6.6. So this first one is really telling me that 6.6 centimeters is to 5 miles. When it comes to the scaling, this is our ratio of what we see compared to what it represents. Yeah? Okay, so we have our ratio, and then maybe we could measure this a little bit here. So, I think all we would need to do for the third one right, is know that we would have to scale it. Let's see, this would be 5 miles. How much would that be? Well, here's our scale. And we have a little bit of work to do, I feel like. Let's see. How tall is this? Well, the height of that is perfectly 1 centimeter. So because this is 1 centimeter tall, I can create the ratio. Let's see, 6.6, I keep doing the same thing, centimeters is to 5 miles, as 1 centimeter is to, oh, it looks like I need to scale this ratio down by 6.6. Hold on. It looks like I'm gonna need to cut this video short right in the middle of this example and come back to it in the next video.